Hello everyone, welcome to A plus BI. This channel is all about complex numbers, and in this video we're going to be solving an exponential equation with complex numbers. We have e to the power z equals 1 plus I, and we're going to be solving for z values. If you're new to complex numbers, go ahead and check out my lecture videos. If you like algebra, number theory, and trigonometry problem, tiny bit of geometry, go ahead and check out Math, cyber with an S. Great, so let's go ahead and see how we can solve a problem like this. I know some of you are probably thinking, why don't we just ln both sides? And that's what we're going to do first. Let's go ahead and start with the original problem, e to the power z equals 1 plus I. And then let's go ahead and natural log both sides. Something to think about is when you find the log of a complex number, the natural log of a complex number. Usually log is used for complex logarithm, log. So I'm going to try to get used to that because I think a lot of people are used to that notation and they say that, yes, you have to use that type of notation. So here's what I'm going to do. I'm going to go ahead and ln both sides, okay? And then I'm going to go ahead and bring the z to the front. Actually, I said that I was going to use the log on the right-hand side, right? So how can you have an ln equals to a log, right? That's the weirdest part. Anyways, let's forget that. I'm just going to ln both sides because I'm not used to it. And then this is going to bring down the z, and z ln e is 1, so it's just going to be z equals ln 1 plus I. But the million-dollar question is, what is the ln of a complex number? Or if you want to write it as log, that's fine. Okay, we can change it now to log. And in this case, log is basically the complex logarithm. Let me go ahead and write it down so you don't get confused like me with the base 10, because base 10 is log. And I just made a video for CyberMath which contains log, which is log, right? So this is kind of like a weird way to write it for me. I got to get used to it, but anyways, you get the idea, right? So how do you log a complex number? That's a good question. So to log a complex number, here's what you need to know. If you can write a complex number as, like, let's say r times, let's call it w, not z in this case, r times e to the I theta, then log of w would just be the log of this, but you can write it as ln r plus I theta. So here's where they kind of, I think, distinguish. When you log z, you're going to have to look at two things. First, the real natural log of the, what's it called? I forgot. Argument, no. Wait a minute, I'm going to remember. Okay, it's modulus, yes, the absolute value. I forgot that term. So the ln of the modulus, and in this case, the modulus is square root of 2 for this number. If you plot it in the complex plane, think about it, you're going to find the hypotenuse. This is theta, which is pi over 4, so on and so forth, right? But it's going to look like this. Well, maybe we should make a bigger picture like this. This is going to be pi over 4 radians, and this is going to be 1 unit. This is going to be I unit, and the distance from 0 would be square root of 2, which is a positive real number. So we can ln that, right? It's a positive or a real log. This is a complex log. This is a real log. That's where the confusion is, sort of, right? Plus I times the argument, which is, in this case, that happens to be pi over 4, so we could probably write it like this. And let me go ahead and delete this. This looks weird here. Okay, here we go. So that should be the answer, right? Or I guess what I meant by this is log 1 plus I is equal to this. Okay, so great. What does that tell you, though? Is that the answer? Maybe. But we could also do this differently, right? Can't we? Because how do we know that this works? Or let's approach this problem a little differently. Obviously, you don't have a formula for log of a sum. Right? That's why you kind of need something like this. But let's go ahead and approach it differently. So we have e to the power z equals 1 plus I. Euler said that you could write any complex number in polar form, which is, again, r times e to the I theta. So why don't we just do that? And if you do it, it's going to look like this. 1 plus I again can be written as, and by the way, here's what you can do. Let me show you the general form. First of all, you find R. If this is W, R is going to be the square root of A squared plus B squared. And then you factor that out, okay? And inside you get A over the square root of A squared plus B squared plus I times B over the square root of A squared plus B squared. And guess what? This becomes the cosine of an angle, and this becomes the sine of an angle. So you can basically write a complex number as, and this is R times cosine theta plus I sine theta. But Euler, thanks to Euler, he is the best, discovered that this is indeed equal to an exponential, which is e to the I theta. So that brings us the most beautiful equation. Isn't that amazing? Think about it, contemplate this for a minute, maybe longer, and you'll just find it mind-blowing. For example, if you replace theta with pi, you're going to get e to the I pi equals cosine pi plus I try to make the pi a little fancy. Cosine pi, as you should know, because cosine 0 is 1, cosine pi is negative 1, right? Cosine pi is negative 1 and sine pi is 0. So e to the I pi is negative 1. Wow, that's amazing, isn't it? Absolutely. And this brings us the most beautiful equation. But I'm thinking about making a separate video about this most beautiful equation. But let's get back to what we have, right? What was I talking about? Well, I was just saying that this can be written as R times e to the I theta. So in other words, there's a way to write this as R e to the I theta. That's where the log comes in. But let's find R, and I think we already did, which was the square root of 2. And then we're going to go ahead and do this. We're going to split it up into this. We need the theta, and we know that theta is pi over 4, right? So now e to the z is going to be root 2 times e to the power I times pi over 4. But here's the problem. Pi over 4 is only one of the arguments, because this number and any complex number basically, I think with the exception of 0, has an argument that can be expressed in infinitely many ways. In other words, if your argument, which is the smallest one in this case, is pi over 4, I mean the angle, then if you added 2 pi to it or subtracted 4 pi from it, you would pretty much be at the same point, right? So that would be the same angle, sort of. So we're allowed to add multiples of 2 pi to this. So let's go ahead and add 2 pi n, where n is an integer, okay? Z is for integers. Now, at this point, you can go ahead and natural log both sides. I think it'll make sense. This will be z equals ln root 2 plus, so you don't have to go into the log, confusing log thingy, I times pi over 4 plus 2 pi n. Again, n is an integer. So n equals 0 gives you the principal value of z, which you can write as ln root 2. And sometimes they're just going to use a capital or uppercase L for this. I'm not really into that kind of stuff because I don't think that's universal. But this would be one of the values and the principal value for the z. But if you use n equals 0, n equals 1, n equals 2, whatever, you're going to be getting different values. The one thing that doesn't change is going to be the ln of square root of 2. And guess what this means? This means you were able to express this number as a plus bi. Isn't that cool? Because it's also the name of this channel. So could we not get there by just naming z a plus bi? Probably. You can think about it and use the idea. Of course, a and b are real numbers. That needs to be in place. So if you replace z with a plus bi, I guess this should be another method. You would get something like this. And then you can separate it into e to the a times e to the bi. And then you could write this as e to the a times cosine b plus I sine b. Now, this is not the end of it. This is the fun part. Then you're going to distribute, right? And you're going to get something super duper nice because this is equal to 1 plus I. Now, two complex numbers are equal. Notice we haven't gotten into any type of like polar form stuff, no trigonometry, a little bit of trigonometry, yes, tiny bit, but we didn't use any argand plane. So we didn't get into any complications, no ln, nothing, right? This is the coolest part. So if this is 1 and this is 1, then we'll be in good shape, right? But wait a minute, is that possible that these two are both equal to 1? Absolutely. That just means that they're equal to each other. And since e to the a is not going to be 0, we can safely cancel that out. And this gives us sine b equals cosine b. Of course, the smallest angle that satisfies this is just going to be pi over 4 or 45 degrees. And from here, wait a minute. How do you get the a value, right? Of course, you know that e to the a cosine b is equal to 1. And you know that b is pi over 4. So cosine of pi over 4 is just going to be root 2 over 2. So from here, e to the a is just going to be root 2, and a is just going to be ln root. You see, everything falls apart once you know to replace z with a plus bi, which helps in most cases. And this brings us to the end of this video. Thanks for watching. I hope you enjoyed it. Please let me know. Don't forget to comment, like, and subscribe. I'll see you next time with another video. Until then, be safe, take care. Don't forget to check out CyberMath and aplusbi, and bye-bye.